In this episode, we'll look at creatures learning to drive. And the episode can be viewed as a response video to CodeBullet's recent video on the same topic. His video is, as usual, very entertaining and he tackles several quite difficult subjects at once. Kudos for that. I was planning to make a video on this topic and this seems like a good opportunity. For this episode, I'll solve the problem using Neat, a technique that CodeBullet has previously used in several episodes. I think it can be interesting to contrast the two techniques. My implementation is coded in C# and Unity. I stole the track design from CodeBullet's video, I hope he doesn't mind. The car graphics is from Kenney. For the learning algorithm, I'm using a Neat implementation I recently coded up in C#. It's actually my second implementation. I coded my first implementation in 2003. Yes, 16 years ago. Yikes!
Daddy, did you even have TVs back then?
No, son. We used to watch TV on a rock. In his video, CodeBullet talks about the evolutionary process being wasteful and he hints that Q-learning would be more effective, which generally is true. But evolutionary algorithms are more than up to the task of solving this particular problem. My implementation struggles with the first turn to the right, same as his did. And then struggles even more with the first turn to the left, same as his did. But it only takes minutes to move beyond both. I'm also artificially making the problem harder by severely limiting how long the creatures have to make it around the track. If they're unable to make a lap in 30 seconds, they're stopped and a new generation is started. This is because I'm impatient and because I'd rather have a fast unsafe car than a slow safe car. His implementation takes hours to find a working solution, but I think the main problem is that he runs a single creature per generation. This is wasteful because the CPU is comfortably able to simulate 150 creatures at once, and as such generate experience at 150 times the speed. This version learns to navigate the entire track at breakneck speed within minutes of starting, and running these cars singly would have taken many hours. The time to solve can be shortened by running the program in turbo mode, which means that we try to run physics 10 times faster. Looks a bit shit, but learns fast. A working solution can be found within 1 minute and 20 seconds. Now, CodeBullet wasn't aiming to create the fastest learner, instead he aimed to learn some new techniques for himself, Q-learning, so our results aren't comparable. I look forward to seeing what he uses Q-learning for next. Back to Q-learning being more effective. Recent results indicate that deep neuroevolution genetic algorithms are a competitive alternative for training deep neural networks, quoting from the paper linked below. The experiments demonstrate that genetic algorithms are a competitive alternative in reinforcement learning to other well-known algorithms, sometimes performing better and sometimes worse. If you have very large computation capabilities, genetic algorithms can be a competitive solution when it comes to wall time to evolve a solution. But genetic algorithms probably can't be competitive if you're comparing how much computational power is used to reach the solution. These results weren't obtained using Neat, but other kinds of neuroevolution. I personally doubt that genetic algorithms could ever beat the best StarCraft player in the world, the way that DeepMind recently did using Q-learning based approaches, because a good gradient descent solution will be vastly more computationally efficient. But evolutionary algorithms have a vast advantage over Q-learning when it comes to simplicity. You can code up a naive genetic algorithm solution in hours, literally. Most cue learning solutions, especially one of the more modern techniques, are much harder in comparison. The color of the car indicates which species it belongs to. There's a species list in the top right corner. The winner from the previous generation is always present in this generation and is indicated by a lemon donut on the truck bed. Note how there's a bunch of really fast cars at the front of the race, but the winner from the previous generation is lagging behind them. This is because fast cars fail in this corner and are overtaken by the eventual winner. If they were able to navigate that corner, they would probably be very successful, but that will take a few more generations if their species survives at all. NEAT was deliberately designed to preserve diversity, to keep species around even though they have poor fitness. This gives them a quiet period to refine their strategies that might start out risky but eventually become winning strategies. Haha, loop the loop! Probably not the fastest way around that corner, but it works. Evolution isn't about the best solution, it's about a good enough solution that gets the job done. You only ever have to beat the competition. As you may be able to tell, evolving this stuff is an absolute hoot. A hoot in this context means fun. It's fun. Actually, I often stop programming and just stare at the system coming up with new and crazy strategies. This is what this run looks like after 300 generations. It's become really fast, and the loop-de-loop has gone away. I miss it. This weird wiggling behavior shows up in multiple separate runs. I'm unsure why, but it makes me suspect that there is some kind of advantage. Now for some technical descriptions of how this works. I'm using the 2D physics engine that comes with Unity, which is based on Box 2D. I use two edge colliders to describe the sides of the track, the barriers. If the car at any time intersects with the barrier, it dies and it can no longer collect rewards. To detect how far along the track that the creature has come, much like Code Bullet, I add reward gates along the track and simply count how many gates the creature has hit. For the car physics, how steering and acceleration interacts with the car, I use a simple implementation that I found in the Unity forum, see the link below. The score, a higher score means a less fit creature, is scaled to 100, where 100 means having hit no reward gates and 1 means having hit all reward gates. To go below 1, the creature needs to navigate the track fast. A number of 0.8 means that all reward gates were hit and that the creature finished the track in 80% of the available time. Here are a couple of runs that I recorded in case you find it as hypnotizing to watch as I do. That's it for this episode, and as always, thanks for watching.